So, Jason from NASA.
Thanks, Steve. At least I'm smart enough to not rely on the wireless network during my demo. So we have a pretty large Lustre installation at NASA Ames. There's about 12,000 clients accessing about 7 petabytes of formatted space on Lustre. But no matter what the size of your Lustre install, it's important to have actionable performance and troubleshooting data. And we think it's important to also have that at interactive speeds, especially if you're doing some visualization of the data, or you're interested in looking at trends that might be very short-lived. So there's a lot of data that you can get from the proc file system and the Lustre kernel debug logs, but there's a few issues with that. First, there's some performance problems at scale if you want to gather data from many OSTs on a OSS serving a large number of clients. In terms of sampling the logs you get from LCUD to DK, you can pollute the logs, and if you're sampling them at a regular interval, you might lose some information that's critical for analyzing, say, a crash dump after a crash. But most importantly, we want more information than we can get from the proc file system. So typically, you might add some new metrics to Lustre by modifying Lustre itself, build, install, reboot a server. But we don't want to do that. So instead, we use SystemTap to generate new metrics on the fly. SystemTap provides system-wide tracing capabilities for both kernel and user space, that we've only used it for the kernel so far. The general process is you write a script in the SystemTap scripting language. SystemTap translates that into C and loads that into the kernel as a module, and then it has a runtime to facilitate transporting output from the script to user space. And one way to look at this is if you consider strace. Strace allows you to trace a process in the tree of children underneath it. SystemTap provides visibility for not just system calls, but calls within the kernel itself across the entire system. Using SystemTap with Lustre is pretty easy. One of the most difficult parts, though, is deciding where to probe for information. You do need to have some understanding of how Lustre works. If you look at understanding Lustre file system internals from Oak Ridge and various people formerly from Sun and now elsewhere, mostly Wham Cloud, it's a good high-level overview, and that plus C-scope and spending some time digging around the Lustre source code will help things out. So the typical mode of operation is you extract data from kernel function calls as they are called in return. And depending on what you're looking at, you'll either output as you go if you're interested in data on a, say, per RPC basis, or maybe you're going to aggregate the data and periodically display if you're interested in, say, the latency distribution for a particular set of calls inside the Lustre code. Something that makes doing this really easy is the fact that Lustre service threads handle RPCs from start to finish and one at a time. So you're always guaranteed that one service thread is going to handle a single RPC before moving on to the next. And so if you're interested in storing timing or other information, you can key that off of the PID of the thread. And so here's, this is the only code in the presentation. Does this have a laser pointer?
Yes.
It does. Okay, I'm laser pointer impaired, so I'll just go through this line by line. So SystemTap will normally infer the type of variables, so you don't have to declare them, but with aggregate types you do. So we'll store start times, and then there's the times variable will be a statistical aggregate that will let us calculate things like a histogram or count, min, max. The next thing that looks like a function call is a probe, and you specify the module and function that you want the probe to fire at and some code to execute when that function is called. So the first one is called when the block allocator is invoked, and the second one's called when the block allocator returns. And so when the block allocator is invoked, the script will store the current time in milliseconds. When it returns, it will calculate the delta and store the result in the times aggregate. And if I hit Control-C to end the script, I'll get a log scale histogram that looks like this. I don't remember the Bugzilla I did this work for, so we were looking at delays and writes on our system that turned out to be due to very heavy fragmentation on the disk and the way that LDiskFS looks for new chunks of free blocks, and also the fact that with OSS read cache turned on, there's a lot of there's a lot of churn in the page cache that will cause the blocks with the block bitmaps and the buddy bitmaps that correspond to them to be discarded and necessitate them being reread back into memory. And so the allocation at the bottom took somewhere between 32 and 64 seconds to complete. So I'm going to go through a few examples of tools that we have written in order to address some problems that we have on our production file systems. The first is addressing poor choice of stripe count. So we decided to make the default stripe size on our file systems 1. Now, since most of our files are relatively small, this is usually okay, but there's two big problems that this causes. First, we ask our users to tar up directory structures that they're going to copy over to our archive system before doing the copy, since our archive system is not going to deal well with a very large number of inodes. If somebody creates a multi-terabyte tar ball, which has happened on multiple occasions, that can take up a significant portion of an OST, possibly filling it. Another common problem is if you don't set the stripe size before, or when you create a file, and you have many MPI ranks writing to a single file, or a file on a single stripe, that OST is going to perform very poorly and impact other users. So we wrote a tool to deal with the first problem, and it's not a big stretch to deal with the second one. A tool I'll talk about in a few more slides will address that a little bit. And so what we did was wrote a SystemTap script and a corresponding Python wrapper that hooks into the write path in Lustre, I think in particular filter prep.rw and filter direct.io, and grabs out various pieces of information that are useful in tracking down the node and process that's writing to a large file. And so I won't run off the list, it's right there. And when a write puts an object over when a write occurs to an object that's over a predetermined size, we'll output that information, and then a Python wrapper script will gather some information about the object and the writing process, including the path of the file and the stripe count. And so if I run this, I get some output like this. And so the time of the event, host name, the OST that the large object is on, stripe count of the file, the PID and name of the offending command, the size, which in this case is about 500 gigabytes, and the path of the file. And so we have a 24/7 operations team that can go and look at an OST that's filling up, and in real time find out which file and which file is filling up the OST, and the host and the command that's filling it up. And so they can go kill the command, move the file, or restrike the file and notify the user. If the command that created the file is not running anymore, you have to resort to some other techniques. And for us, that's usually running E2 scan to find the large object, and then you can use the debugfs ncheck command to go and find the corresponding inode on the MDT and its path. So another issue that we have to deal with is fragmentation, and in particular two sources. One is on-disk fragmentation. As I described before, the block allocator sometimes won't find a large enough chunk of contiguous free space, and just the process of finding a chunk of free space can take a long time, and if it results in fragmentation, you have additional IOs for the write itself, and then additional IOs for the read when you read the file back into memory. Another source of fragmentation is an IB SRP driver. I'm not going to describe this at length. Dave Dillow gave a talk about this and a solution at the Open Fabric workshop in March. May's not here yet. And you can go watch it online, but in a nutshell, you can only have 255 lists of pages describing an IO on an OSS that's going to be sent to an SRP target. So if you don't have at least one pair of contiguous pages in memory, you end up with a 1020 plus 4K IO. And this will cause performance problems. We've seen in a recent test about a 30% degradation in performance due to this. And so this tool is not as refined as Big Object is. It's just raw output from SystemTap. But what you get is the node that's performing the I/O, the OST. I'll explain why UID and MDT inode are 0 in a moment, and the size of the I/O. So the first one's going to be a 1 megabyte or larger I/O. There's 256 entries in that, or 256 pages in the I/O. The second one's an example of memory fragmentation that's going to cause SRP to issue multiple I/Os. So the first I/O is of size 255 pages, and there's, in parentheses, the number of hardware descriptors. There's 255, and the second one is just a single page. So we did some maintenance on some of our servers recently. Afterwards, we typically run IOR to ensure that we can get those coveted hero numbers, and typically that's a very good indicator of things going wrong at a high level. So it'll point out IB issues, configuration problems, and in this case, 1 out of 8 OSSs for this file system somehow ended up in some pretty severe memory fragmentation that this script showed immediately, and we just rebooted that OSS before it went back into production, and that fixed the issue. And then the last example here is of on-disk fragmentation. So the first I/O has 6 pages in it, and the remaining all have 1. And so the next step for this is to aggregate this data based on a per job basis, so we can go identify codes that are suffering from memory fragmentation issues on the OSS, and also codes that are suffering from on-disk fragmentation, and we want to go and fix the codes that are causing that on-disk fragmentation due to poor access patterns. So the last tool I'll talk about helps us identify the source of high OSS load average. We found it's typically due to long disk queues. There certainly are other causes. And the long disk queues are usually caused by many hosts performing I/O to a file that's on 1 or a small number of OSTs. And again, remember I said that on our file systems we have a default strike count of 1, so this is actually a pretty common problem in our system, and maybe a good reason to change that strike count to something higher. Now, you can mine the data in proc to find out the source of the offending I/O. Again, on a large system, this takes time, and beyond that, I'm interested in knowing which file is being accessed. Now, you saw in the previous example here, for some of these, the MDT, inode, and the UID are 0. There's a, struct OBDO. In some cases, it looks like it doesn't have those fields filled in, and it might be on purpose, it might not be. I haven't gone and dug into this too much yet, but if that data is there, I can identify the file being accessed for both reads and writes, and pin down or drill down to a per file level, which is great to have because now I don't have to go to a node that's generating a lot of traffic to a single OST or set of nodes. I can go back to our scientific consulting group and the user and say, hey, I/O to this particular file is causing problems. You need to stripe it across multiple OSTs, or we need to look at your access patterns to improve them. And so that's really useful versus just giving them a job number and a time that a problem occurred at. And so the output of this command is a little icky to read. It's very similar to IOStat, except I've clipped some columns out so it would fit on the slide, and there's 2 extra columns on the right-hand side. So there's the job number or host that generated the highest number of read plus write RPCs during the sampling interval, and the count. And we can update this at a very high rate, so typically run it at a 1 second interval. So I'm working through the NASA open source process. I'm hoping to have all the paperwork done shortly after I get back, and the distribution will include a few things. First of all, SystemTap allows you to collect a set of aliases for probes and code to extract common data into a library called a tap set. And so there's a tap set that'll, along with some documentation, that will help ease the process of developing tools that use this technique. There's the big object in OSTstat utilities, and if I finish the wrapper around the fragmentation utility, that as well. And then I recently rewrote all these from Perl to Python, first of all, to clean up my code so I won't be too embarrassed when distributing it. But second, to remove some site-specific issues or site-specific dependencies, and one of those is the batch system that we use. So there's an easy hook that you can use to map host to your site's batch system. I'm really interested in expanding this technique. If you have ideas for tools or problems that you think that can be solved by using this technique, I'm interested in hearing about them. And once this is made open source, if you can send patches, that's always appreciated, of course. The last thing I want to talk about is visualization. So especially for the latency distribution of function call times, interested in looking at heat maps of those call times. And so the idea is if you look at a hierarchy of calls from top to bottom, visually it's going to make it easier to pinpoint where in the stack you might be having some performance problems. Now you obviously can't look at latency distributions for all of the calls at one time, so you have to be selective in what you display. So it's a bit of an iterative process. And so what I've done over the past few days is whipped up a quick demo. I guess it's somewhere between a mock-up and a prototype. So the visualization is live. The data was collected from a live system but is being played back again because I don't trust the wireless network during my talk. And so I'm showing, I don't remember the exact name of all the calls here. The Lustre, the names here are actually the names for aliases in the tapset library, but it's the function that OST handle calls the very top level of handling a write RPC. The second one is filter do BIO, and the last one is the same that I showed the script for earlier, the LUG block allocator. And the oranger a square is, the more calls show up in that bin. There are no labels in the axes yet, but the x-axis is time, and the y-axis is log scale in milliseconds of the latency for that particular bin from 0 to 1 up to a second plus. And I didn't try and create a very interesting, well, I tried to create an interesting situation. It didn't create that interesting data. This is from a relatively idle file system, fired up IOR on 128 ranks pitted against a single OST. And you can see that the writes are pretty slow. Most of them are between a quarter of a second and a second plus. And some of those are, some of the slow performance is a result of the block allocator. So you can see some of the white vertical lines in the latency heat map for the block allocator, but not very many of them. And so you need to go dig a little bit deeper and look at other portions of the write path to understand why the performance is slow. And it may simply be the writes to disk because the queue is overloaded with requests because I'm hitting it from hitting the disk from so many clients. So this is where I'm trying to make things go. Again, the interface is very crude here. I've only been working on this for a few days. And this is largely inspired by some work done by folks at a company called Joyent that are formerly from Sun and Oracle that did a lot of work on dtrace that are using this to, again, do real-time heat maps of not just latency but some other metrics as well in order to aid in finding and fixing performance problems. So a few references, and of course the slides will be available, so you don't have to write that down. And if you have any questions, if there's time now, or find me afterwards or shoot me an email. Thanks.